Welcome to our 1.2 video on biconditionals and definitions. Our essential question is, how can we use biconditionals to write good definitions? So first we have some vocab on biconditionals. So a biconditional is the combination of a conditional statement, P implies Q, and its converse, Q implies P. And we combine them with the words if and only if. We also use IFF as an abbreviation for if and only if. So I'll use that below. The symbolic form is a double-ended arrow. Sometimes we use 2 lines for the arrow. Sometimes we use 1. Okay. Next, we're going to talk about what makes a good definition. So good definitions use clearly understood terms. The term should be commonly understood or already defined. So either something that is commonly known or you've already defined the terms in class. Number 2, it should be precise. Good definitions avoid words such as large, sort of, and the same, or in some. And 3, it should be reversible. You can write it as a biconditional. So writing biconditionals is a key part of a good definition. Okay, example 1 says, consider the true conditional statement, write its converse. If the converse is also true, combine the statements as a biconditional. So the conditional is, if x equals 5, then x plus 15 equals 20. That's true. If we write the converse, if x plus 15 equals 20, then x equals 5. This is true. Because math, we could solve it. We subtract 15 from both sides and we get x equals 5. So we know that that's true. And we can rewrite our biconditional. I've used the IFF abbreviation for if and only if. So I say x equals 5 if and only if x plus 15 equals 20. Next, for the try now, you're going to do the same process. Write its converse, determine if it's true, and then write the biconditional for if 3 points are collinear, then they lie on the same line. So pause the video now and try this one. Okay, let's talk about it. So the converse is if 3 points lie on the same line. Notice I moved that subject again. I left the 3 points in the beginning, even though I switched the hypothesis and the conclusion. If 3 points lie on the same line, then they are collinear. That's true by the definition of collinear, and the biconditional would be if 3 points are collinear, if and only if they lie on the same line. Example 2 says, write 2 statements that form the biconditional. So our biconditional is lines are skew if and only if they are non-coplanar. So I can break this up into the original hypothesis, or the original conditional statement and its converse. There's no way to tell which one was the original conditional and which one was the converse. So if you have the same 2 statements but they're just flip-flopped, that's fine too. So conditional, this could also be in your converse spot. If lines are skew, then they are non-coplanar. And then if lines are non-coplanar, then they are skew. Again, if you flipped those, you're still right. Okay. Now, here's your try now. So you're going to write the 2 statements that form the biconditional for a number is prime if and only if it has only 2 distinct factors, one in itself. Pause the video now and try it. Okay. Next, the conditional that I had was if a number is prime, then it has only 2 distinct factors, one in itself. And the converse that I had was if a number only has 2 distinct factors, one in itself, then it is prime. Again, flipping those is just fine. Okay, example 3. Show that this definition of a triangle is reversible, then write it as a true biconditional. So the definition is a triangle is a polygon with exactly 3 sides. So I can write the conditional. If a polygon is a triangle, then it has exactly 3 sides. That's true. If a polygon has exactly 3 sides, then that's a triangle. That is also true. And so we can write a biconditional. You can only write biconditionals if both the conditional and the converse are true. And that biconditional is a polygon is a triangle if and only if it has exactly 3 sides. And the try now is the same, so we're going to skip that. Example 4 says, is the following a good definition? Explain. An apple is a fruit that contains seeds. Well, that's not a great definition because we know there are other fruits that contain seeds. That's not describing only apples. So we can say it's not reversible because we couldn't write the converse, right? We could say the conditional, if you have an apple, then it contains seeds, but we couldn't say if it contains seeds, then it's an apple. So it's not reversible, and a counterexample is oranges have seeds inside them, and they are also fruit. Try now. So determine if this is a good definition, and explain. Okay, you should have paused the video. We're going to go through it now. Again, this one is not reversible. We can say a rectangle has four right angles. So though we can say if it is a square, then it has 4 right angles, we cannot say if it has 4 right angles, then it's a square. It might be a rectangle that is not a square. Okay, that concludes our 1.2 video.